Dear students, Assalamu alaikum. This is going to be our lecture 17 for Engineering Fluid Mechanics 2 to 5. Today we will do a review of the control volume and system approach. We will see an example for the Reynolds transport theorem. Then we will derive the conservation of mass for a control volume using the Reynolds transport theorem. So we start with our lecture. Uh, First, we will do a review of control, volume, and system approach. Again, we will first define the system. System basically is a collection of matter of fixed identity that may move or flow or interact with the surroundings. Uh, Last time when we defined the system, or when we studied about the system in last lecture, we discussed a volume of some fluid that is being pumped into the compressor. We could probably die some volume of the fluid that is going into the compressor. So that fluid might come out of it with the difference in temperature or difference in shape, but it will still define the same system. Contrary to that, we have the control volume approach, which we define as a fixed region in space through which fluid might flow. The matter in control volume may change over time as fluid flows through it. You can see a screen on your you can see a picture on your screen that is probably a variable area duct where we have selected some part of it to be the control volume. So we define the control surface, the dashed line which is defining the control volume is the control surface, and control surface is defined as the surface surrounding the control volume. It is very important that you get yourself familiarized with these terminologies so that you can communicate and understand the problems and then attempt to solve them. So moving on, uh, we'll also do a review of the Reynolds transport theorem. The most general form of the Reynolds transport theorem is on your screens at the moment. You can see it. The terms, the definition of all the terms that are there in the Reynolds transport theorem is on your screens now. The first term basically is the time rate of change of extensive property B of the system. So what is the quantity of B in the system is actually equal to the total derivative of dB sys over dt. Then the rate of change of B in the control volume, and then net flow rate of B across the control surface. We also discussed about the uniform flow, which we define as if the velocity V is constant over the area A. So this is the area, and velocity V, we can see that all these vectors are of equal length. So that's how we define the uniform flow. Contrary to the uniform flow, if we have a non-uniform flow, then the velocity V is a variable over the area that is being depicted by the length of these vectors in this figure. So if the flow is uniform, then we can simplify this integral to be a summation with which will be defined as b into rho v dot a. If you remember the last lecture, we derived the continuity, or sorry, we derived the Reynolds transport theorem with the help of a variable area duct by assuming a control volume in a variable area duct. And there were two pictures, one of a control volume and one of the system. So basically the control volume remains fixed and the system moves some volume of fluid flows into the control volume, and some volume of the fluid flows out of the control volume while the system travels. So we labeled one to be the inlet of the system and two to be the outlet of the system. It is important to discuss over here that the inlet is negative over here, and the outlet is positive over here. That is because of the definition of this dot product V dot A. Basically, velocity vector V and A are such that at the outlet they are linear, and the angle between them is 0, and their dot product comes out to be positive. At the outlet, at the inlet, sorry, that is for at the outlet they come out to be positive. At the inlet, uh, they are in they are still collinear, but they are in opposite direction. So there is an angle of 180 degrees between the area vector and the velocity vector. That is because of the definition of the area vector. We define area vector to be pointing out of the control volume and always normal to the surface. So at the inlet we have a negative uh, flow, or we represent the quantity by negative. Okay, so these kind of summations are very useful if we have if we have a problem like that where we have many inlets and many outlets. Then all these inlets and outlets, they can be written as a summation of all the inlets and outlets. But we must remember that inlets we must always take as negative, and outlets we must always take as positive. So now we will see a problem related to the Reynolds transport theorem. The problem statement appears now on your screen. It is being told to us that two plates are pulled in opposite directions with speeds of 1.0 feet per second as shown in figure P4.70. The figure is over here. We can see the plate, the upper plate, it moves to the right with a velocity of 1 feet per second, and the lower plate moves to the left with a velocity of 1 feet per second. There is oil between the plates. The oil between the plates moves with a velocity given by V is equal to 10y I hat feet per second, where y is in feet. So the velocity is basically just u velocity, and it is function of y. Uh, the fixed control volume ABC, which is being represented by this yellow dashed line in this figure, coincides with the system at time t is equal to 0. So this dashed yellow line represents the control volume for all the times, but it represents the system for time t is equal to 0 as well. Now we have to make a sketch to indicate A, the system at t is equal to 0.2 seconds. So we know that the system will keep on moving while the control volume will remain fixed in the space, and the system will move with the flow. And so we have to tell how will system look like after t is equal to 0.2 seconds. The fluid, and in part B we have to tell whether the fluid that has entered or exited the control volume in this time period. So with the sketch we have to show that which fluid has left the control volume and which has entered the control volume. So to start with, we know that velocity is on the a function of y, and we have only x component. You can also see this velocity profile over here in this figure as well. So at the plates, oil will have a velocity of 1 feet per second. At the upper plate it will have a velocity of 1 feet per second to the right. At the lower plate it will have a velocity of 1 feet per second to the left, and at y is equal to 0 the velocity will be 0. So we just have to find out that just a moment. Yeah, so we just have to find out that how these 4 points that I am highlighting now in this diagram, how these 4 points move, and then we can define that how will the system look like at t is equal to 0.2 seconds. So the lines A, B and C, D, we will draw them. Again, the figure appears now on your screen. So what has happened is, initially we had a line AB like that. So with the upper plate moving to the right, point B will move, but how much this point will move in 0.2 seconds? The velocity of oil at this point is 1 feet per second, and if this point moves for 0.2 seconds, how much it will move? It will move 0.2 feet. So this is actually, the distance is 0.2 feet. So B has moved to B prime, which is 0.2 feet away. Similarly for C, C also moves to the right to C prime, and the distance is the same, 0.2 feet. For the lower plate, point A, it moves to the left, and A goes to A prime in the same manner. That this point will also move with the velocity of 1 feet per second, and will travel 0.2 feet in 0.2 seconds. D travels to D prime, and so we have this small dashed line represents our system at t is equal to 0.2 seconds, which we were supposed to show at time t is equal to 0.2 seconds. Also, we have mentioned the volumes that flow into the control volume, and the volume of fluid that flows out of the that has flown out of the control volume in this time period. So this dotted area, both these dotted areas, they are the areas which flow out of the control volume, and these areas with lines, these are the areas which flow into the control volume. So now we will see that how we can derive the conservation of mass via the Reynolds transport theorem. So we um, assume B to be the mass of the system, then as B is the extensive property, as this B is the extensive property of the system, so we'll have a corresponding intensive property, which will be capital B divided by mass of the system. This will give us small b, which is the intensive property of the system. B is equal to 1. So we will use this thing, use capital B is equal to mass, and small b is equal to 1 in our Reynolds transport theorem, which we have just reviewed earlier in this lecture as well. Here is the equation. So instead of this b, we'll have 1 over here, and this will be dm over dt. So here is our Reynolds transport theorem with P is equal to mass and small lowercase b is equal to 1. We have now the terms appear which actually define what these terms are. So the first term dmc over dt actually is the time rate of change of the mass of the coincident system. So if you see figure B over here, this figure we are talking about, at this point the control volume and the system are coincident, and at this point this term gives the rate of change of mass inside the system. This term, the second term, this is the time rate of change of the mass of the contents of the coincident control volume, and the last term is actually the net flow of mass through the control surface. So what is flowing in and what is flowing out of the control system, sum of these quantities, and if the net flux is out, it is taken as positive. If the net flux is in, it is taken as negative. So we know that system by definition is a collection of matter of fixed identity. So the number of particles, or the particles that define the system, they will never change. This means that the mass of the system will never change over time. That's why dmc over dt will be 0. So with this information, the continuity equation, or the law of conservation of mass, that is how it is most commonly known, for a control volume can be written as dava over dava t of integral over control volume of rho dv plus integral over control surface of rho v dot n hat dA, where n hat is the unit normal on the control surface, and the unit normal n hat points outward of the control surface. Now we say that in the same manner what we did for the Reynolds transport theorem, if we have a uniform flow or one-dimensional flow, then we can change this integral over the control surface to a summation over the control surface, and this figure actually shows us why the inlet will be negative, because v dot n hat n hat is the vector unit vector for a over here. So this is n hat is the unit vector for a over here. So v dot n hat will be less than 0 at the inlet, so that's why inlet will be negative, and v dot n hat will be greater than 0 over here. That's why outlet will be positive. So this summation can be written as summation of rho va out minus rho va in, and this will be 0 if we are assuming steady state. This means that dava by dava t rho dv, or the rate of change of mass inside the control volume, will be 0 in a steady state problem. So this means that m dot out minus m dot in will be 0, or m dot out will be equal to m dot in. So in a steady flow, we can say that what flows in will always equal what flows out. Additionally, if in addition to flow being steady and one dimensional, additionally if the flow is also compressible, then the law of conservation of mass, which we have written as m dot out is equal to m dot in, can be written as va or va out is equal to va in, which is volumetric flow rate at the outlet will be equal to volumetric flow rate at the inlet. So if it's an incompressible flow, to then to define the law of conservation of mass, we can just simply say that the volumetric flow at the outlet and the volumetric flow at the inlet are the same. These are the practice problems for you from chapter 4. I hope you will be able to do them. If not, you can always discuss them with me. Thank you. Allah Hafiz.